Today we are going to start a very important topics for Iit-Jee and Neet preparations, and this is very important. That topic is Doppler's effect of sound. Normally, Doppler's effect of sound is applicable to the waves, whether it is sound waves or the light waves. So we are discussing this only here. In this case, a sound wave. So Doppler effect in sound wave, whenever a source of sound or a observer is moving, the frequency of the sound appear to the observer is changing. So this changing of the frequency known as the Doppler's effect. So here the Doppler effect, when both are, there are many cases of the Doppler effect. When both are at stationary, when the source of the sound and the observers are at stationary, then there is no change. When there is no change of the frequency, whatever the original frequency of the sound will be heard by the observer as the same one. But whenever there is a relative motions between the observer and source, the frequency appear to the observers will change. It means that whenever the separation between these two are changing, I mean that when the separation between these two are decreasing, the frequency of the sound will be heard by the observer is decreasing. That decreasing is different one. Whenever the source is moving toward the observer, the frequency, if you measure the frequency, and when the observer moving toward the sources, if you measure that frequency, both frequencies are different. But these two frequencies are the same, as not as the same, but they are different from the original frequency. The frequency in both the cases will be more than that of the original frequency, but these two frequencies are not same one. That's why the Doppler's effect in sound is not symmetrical. But in case of the light, the Doppler's effect will be symmetrical. It means that whether the source is moving toward the observers or observer moving toward the source, in case of the light waves, the frequency will be the same, but in case of the sound it will be different. Let us discuss one by one. First one, when the source at stationary, observer is stationary. So we know that the source is a point sources. It will emit the wave in the form of the spherical wavefront. So it has a spherical wavefront. These are spherical wavefront. The source of sound is stationary, observer is stationary. Whenever it's sending the spherical wavefront toward the observers, the space between the spherical wavefront will be the same. Whatever the space between the wavefront at the point of the source of sound will be same as when these wavefront approaching to the observer. That's why the frequency which appear to the observers will be the same as the original frequency of the sound. So in that case, we can say that the observed frequency, I mean by the observers, also known as apparent frequency, will be the same as that of the original frequency when both are at stationary. Here have a apparent frequency, and FO known as the original frequency of the sound. So in this case, when both are at rest, there is no change of frequency as heard by the observer. Now one by one we go in the second case. Observer is at rest, but source is moving toward this one. Now in the second case, now the case number seconds, when sound source and observers are moving towards each other. So here in that case, whether the source of sound moving toward the observers or observer moving toward the source of sounds, in both the cases the frequency will appear to the observers is which are encouraging. So because when the source, when the distance between, whether anyone can move towards each other, yeah, both can move, yeah, one is stationary, another moving, and if this is stationary, this is moving toward the observers. In both the cases, since we know that this is a point source, this is a point source of the sound, it will emit spherical wavefront. It has a spherical wavefront. We know that the distance between the spherical wavefront toward the observer is decreasing. The space between the wavefront is decreasing. In this side it's a larger one, and this is larger one, and in this side is smaller one. Whenever the wavefront going toward this one, whenever the wavefront is emitted by the sources, and the source is also moving toward the observers, so in that case the space between the spherical wavefront toward the observers will decrease. But in that case of the far away from the observer, in this side the distance between the wavefront will decrease. That's why the frequency which heard by the observers appear to increase. It means the frequency, by the definition, so we know that the number of waves in a 1 second known as the frequency. So the number of waves between the source and observers will appear in the same time as the earlier one. So in that case, let us suppose F is apparent frequency, FO original frequency. It has 1 by we can go with two cases. In the first case, source of sound is at stationary. This is our source of sound. So first case, this is the observer. Suppose let us say FO is speed of the observer, and Fs known as speed of source, and V is the speed of the sound wave. Speed of sound wave. We have developed a formula for the apparent frequency in all the cases one by one. First, let us start when the observer at rest and the source is moving toward the observer. How to calculate and what will be the formula for the apparent frequency which is observed by the observer. This is the case when source is moving toward the observers and observers at rest. In the first case, is a normal case when both are at rest. We know that between the two crests, the length between two crests there will be a wavelength. So this is a observed actual wavelength of the sound wave. Between two crests or between two trough also it will be the same ones. So here when the source at rest and observer at both are at rest, in this case source is also at rest. PS means source of the sound, and this is observer. Both are at rest. This is a normal wavelength. So in that case, if I say that velocity of sound is equal to distance covered divided by time taken. If I say that 1 by t, if I take this time taken is 1 second, so then the distance will be equal to the velocity, this one. In first case, if the time taken from the source, in this case from source to observer is 1 second, then the distance between S and O will be V. In V seconds. Suppose if I say that there are FO frequency, FO waves, therefore the apparent wavelength and the observed wavelength will be the same, and it has the value of V divided by FO. Velocity of sound, V the velocity of sound, velocity of sound, and here I have taken the time is 1 second. the numbers of waves passing from source to observer is suppose FO, then B upon FO comes out LO. LO means the original wavelength of the sound wave, and LA means lambda A. Lambda means the apparent wavelength to the observer. In both the cases, both will be the same one. This is our equation number first. In second case, when the source is moving toward this one, velocity of source is not stationary, but our observer at rest. In both the cases, observer are at rest. So here in the 1 second time, same way we are comparing both of these one. In 1 seconds, the same numbers of wave which is transmitted by the source in the first case also will be the same in the second case also. But in that case, the distance between the source and observer is reduced. So we know that in 1 second, distance traveled by the source comes out in 1 second. Vs is equal to d also. So now the distance traveled by this is the distance traveled by the source, and the remaining distance, in earlier case this distance is v. Now the distance reduced is comes from v minus vs. V minus vs will be the distance between the observer and the source in the second case, because that much of distance covered by the source in 1 second. Now from here to here, in earlier case from here to here, the FO wavelength, FO is the frequency, number of FO is the frequency, number of waves transmits by the sounds is FO. In that case also, in second case, same number of frequency will be there in 1 second. So but the wavelength reduced in second case, because the distance between source and observers reduced by a distance of Fs. So in that case, this will be reduced value. This is apparent wavelength between the two crests. In earlier case, between the two crests, the original wavelength LO is more than that of this value, because in that case the source is moving toward the observer, distance between source and observer is reduced. So in that case, and between source and observer, the distance is this one. So in this case, V minus Bs, number of waves, number of the distance between the two crests will be reduced. That value comes out, lambda apparent wavelength comes out V minus V S divided by FO. FO is the frequency. So frequency of the sound will not change, original frequency will not change, but the apparent frequency which is observed by the observer will change, and that value comes out this one. So it means that in that much of distances, FO number of waves are remain there, but the width of this one, but the width of the wavelength, distance between two crests will be reduced as compared to the original one. That's why we have seen higher frequencies of the source. Now if you compare the original value of the original wavelength is equal to V divided by FO, and now the reduced wavelength comes out lambda A V minus velocity of source divided by FO. If you compare both of these ones, it will be lambda A will be less, lambda will be less than that of the lambda O. So now the apparent frequency to the observer will be Fa velocity of the sound divided by lambda A apparent wavelength. If I put the value of lambda A from equation number second, the value comes out B minus Vs divided by original frequency. If you simplify this one, B times of BO, B this FO goes in the numerator and remainder will become this one, B minus Bs. So now apparent frequency V upon B minus Bs into original frequency. So look here, the coefficient of FO original frequency is V upon B minus Bs. B upon B minus Bs is less than that of 1. Therefore, FA value should be greater than that of FO. The apparent frequency of the source which appear to the observer is more than that of the original frequency. Now in the second case, if I put the source at rest and observer moving toward the source, in that case also the frequency will increase, but that frequency will different as this frequency. If we write the apparent frequency is equal to V divided by V minus Vs multiplied by original frequency. Look here, the coefficient of FO is more than that, is greater than 1. That's why apparent frequency will be greater than that of the original frequency. Let us define in another case when observer is moving towards a stationary source. This is our observer and this is our source. In earlier case, this is a normal case when both are at rest. So these are both are at rest. Now suppose in 1 second, if I say the 1 seconds distance will be speed of sound. And 1 second, suppose there are between source and observer there are FO waves. It means that in 1 second the observer received from the source FO waves. Now it means that whenever in 1 second, suppose if you take a point is here, suppose the P point is here, in 1 second this P point is reached to the point of this one. This P point reached to this one, there is continuously wave is coming from source toward the observer in 1 second. At the beginning of the when we counting the times, the P point is at here at t equal to 0, and at the time of t this P point reached at t equal to 1 second, the P point reached at this point, and continuously the wave is coming from these sources, and between backside of this P is also other waves. And in that case, when earlier case the position of the observer is here, now the observer is reached at this point. Suppose the new position of this observer in 1 second. The observer now, in that case, when the observer moving towards the sources, the number of waves which are received by the observers will increase. So because in that case, in the same ways, the earlier case, that much of waves is received, and it also increased more than that of this one. Why? Because in 1 second the observer had traveled a distance of this one. This is distance the observer had taken in t equal to 1 second. So in t equal to 1 seconds, the P point in earlier case at the beginning of time is here. Now this P point reached at this point as in earlier one. So now these waves already received by the observers, plus some extra waves is also received by the observer. How many these extra waves? So these waves, okay, that the new position of the observer, the other position of this one, the distance between them is BO. BO means the distance traveled by the observer in 1 second. So the number of waves is contained by the length of BO will be the extra waves which received by the observer. Now that's why the apparent frequency will be original frequency plus, now the extra frequency will be, this is the original frequency plus the extra frequency which contains in this length will be observer this distance divided by FO. We already know that FO is equal to B divided by lambda O. If I place these values in equation number this, we will get the required apparent frequency. Now place from these relations observed frequency is equal to, this is original frequency is equal to wave of speed divided by the original wavelength. From here, if I calculate the value of original wavelength V upon FO, if I place these values here, I will get FO plus VO divided by V upon FO. Now just simplifying it, VO FO divided by V. Now taken FO outside and 1 plus observer velocity divided by wave velocity is equal to, taken the LCM, if I take the LCM, it comes out V plus VO divided by V multiplied with original frequency. So it means that the apparent frequency, we know that the coefficient of FO is more than 1, therefore FA will be, apparent frequency will be more than that of this one. So here look here, the frequency which appears in earlier case its a value is when the source is moving toward the observer is addressed, our apparent frequency comes out FO B minus FO multiplied velocity of the sound divided by V minus this was. So in that case, these are the two values. One is this one's, another is this one's. Both are different ones. In both the cases, the distance between the source and observer is decreasing and frequency is increasing, but the value of the frequency will be different. In that case, when the observer moving toward the sources, our frequencies, these values. When source is moving toward the stationary observer, our frequency will be this one. In both these values of frequencies are different. That's why we say that Doppler's factor in sound is not symmetrical. So if it is symmetrical, then these should be equal, but these are not the same one. That's why Doppler's fact in sound is not symmetrical.